And we're back here at the main stage. After Internet of Humans, we're going to talk about railways and safety automation on railways. Welcome on stage, Arthur. The floor is yours. So I'm super curious to hear more about what you have to share.
Thank you very much for the introduction. QuantUp does basically two things. The first one, we improve business processes with help of mathematical tools, for example, machine learning. And the second thing, we help to build products with help of the same mathematical methods. And there is Goldschmidt. Goldschmidt delivers product for the railway industry, and this will be a story of a joint project of these two companies. What was the challenge we faced? Now about track inspection. It's very important to have tracks safe, and this is really regulated. So each track needs to be investigated regularly. For example, these main tracks have to be investigated each 2 weeks. What does it mean? It means that a track inspector just walks along the track and check if anything is wrong. For example, the sleepers, fasteners, and so on and so on. It's just needed to be inspected manually. And it's risky for the inspector because of trains going along the track. So it's slow and it's risky. These are the reasons to think about a different approach. So for many years, people tried to build automatic measurement systems and trains. You can see a couple of them, just different kinds. And what data can be registered and how does it work? First of all, this track inspector was not substituted, but they avoided letting the track inspector going along the track. Just the data, the images were recorded and inspected in the office by the same track inspector, but still it was slow. But what data can be stored, recorded? The first one, this one, is just track surroundings, just a general view from the driver's perspective. We can see if the signs are visible and properly located. So just the overview. The second one, the middle one, the most interesting for us, is from a linear camera, just from a special train, to check all the elements of the infrastructure. Railhead, the sleepers, if you don't know this term, are these elements made of concrete. And the most detailed images, just the railhead surface to check if there are some damages or not. What was the problem to solve? When we concentrate on more detailed images, we can observe a couple of things. The first one, a displaced fastener. This is a fastener. If we can locate it, we can fix it with special tools. The second one, it's, for example, a rail joint defect, but it can be a rail head defect. And the third one, the most important for us, are just damaged sleepers. You can see severe cracks along the sleepers. And this was the topic of our project. Let's look more closer at defects. The sleepers can be cracked. The sleepers can be chipped. The sleepers can be covered by ballast. It's not shown, but you can image the ballast lying on the sleeper and the potential defect is not visible. And the last one, the sleepers can be turned or just displaced. But we were not interested in this one in our joint project. And what's important, the part we did with Goldschmidt was a part of a bigger project. Development of this bigger project took nearly 2 years. So it's a part of something important and long-term. So the first step was how to measure quality of results. And it turned out not to be easy. Why? The data scientists want to measure sensitivity, and specificity. You might be familiar with these measures, but it's not that important. More important are these two. So how does it work? If we have just a video recording from the track, the algorithm should give a list. And this list contains information. This slipper is damaged. But the algorithm can be wrong, but still delivers a list of slippers with information damage, damage, damage. And what we need to control, what we'd like to control, is length of this list and how often this algorithm was wrong. So if it delivers a list of damages, some of them are real damages, but some of them are false alarms. And it's simple from business perspective, but if you look from the perspective of a track inspector, they got used to look in a special way at these results. So for them, most important information was something what's called sensitivity. So how many of real damages can be detected? And if they get a list, what number of real damages comparing to the length of the list. And you cannot realize just at the first sight that this measure called precision, the last one I described, it depends on a fraction of damages in the track. What does it mean? You have just fixed one algorithm, you run it for one track with a lot of damages, and you run it for the second track with less damages, and you will see different values. So what was very important in this project to agree upon how to measure quality of the algorithm, what could we guarantee to Goldschmidt and to Goldschmidt clients, and it was very, very important to be understood by track inspectors and by the clients. So this was the first hard element, but it seems to be really simple. You can either be wrong or right about prediction of damage, about detection of damage, but it turned out to be very, very important for the project. So what was the solution? We can say we just built a classifier, three-class classifier, but it's not that easy. It's not that we just took a big neural network and we taught it to recognize these kinds of damages. We built, as usual in these cases, a kind of workflow. So it started from data annotation. What does it mean? We needed to have a sample, just a video from the track, and to mark them. This is a normal slipper, this one is chipped, this one is cracked, and this one is covered by ballast. So this was data annotation. The next step was data preparation. We can understand is as an algorithm wearing, for example, polarized glasses or having an infrared camera. What I mean by this comparison, data preparation was applying some algorithm to allow this classifier that classifies to see more. So this was data preparation. And next comes feature extraction. It means we tell to the algorithm, look at these properties, look at these areas. So this was feature extraction. We used some neural networks, but it's not important. It's completely technology agnostic. And next, we built a classifier. So we have data annotated. We know what's damage, what's normal. We have them prepared to enhance data and to allow the algorithm to see, to distinguish between damage, not damage. We built algorithms that can classify crack, chip, ballast, normal. And what we needed to do is something non-standard, is optimization. The algorithm returned probability of being damaged, and we needed to have cutoffs to decide if probability given by the algorithm should be reported as damaged or not. So this step requires some multidimensional optimization. And what was very important was validation of the algorithm using additional data. For example, we teach our solution on one piece of track and check how it works on another piece of track or on another track. So this was the outline of the method, but I'd like to emphasize just one thing, annotations. It's undervalued. What you can see, this one is normal. It's not cheap. And this one is cheap. This is cheap. So it's not that obvious to teach the algorithm what's normal, what's cheap. This algorithm should detect such small chips, but should not report this as chipped. So it was a tricky part, and they have regulations what is chip, what is not. But human eye cannot distinguish, not trained human eye, cannot distinguish between these two, but we force the algorithm to distinguish between them. So this was very important part to annotate data, to know what's so-called ground truth, and to teach the model. So it's time for a summary. What you can see here are properties of the algorithm. Sensitivity equals to 84% means probability of detecting of damages. We don't care about length of the list I talked about. So we had probability of 84% of detecting real defects. And it can be split to different kinds of defects. When we have critical defects, severe, you can see it's completely broken. We had 89. For example, for chips, we had 81, and it could be justified by the previous slide. You saw that the chips were really, really tiny, and it's not that easy to distinguish between chip and normal. It was really easy to detect ballast, just to detect stones on the slipper, and it was pretty easy to detect long cracks, or just cracks. And what's applicable for startups? This is a conference rather for startups, right? And it was about Goldschmidt. Maybe you know, maybe you don't know. Goldschmidt is not exactly a startup right now. But what's the link? The Goldschmidt group was a startup 100 years ago, but it's not the only link. From my perspective, it's pretty similar. And let me try to convince you why. This product we worked on was something completely new in Goldschmidt's portfolio. So we have novelty. This feature of detection of damages was a very important feature in this big solution for Goldschmidt clients. So we have impact. And traditional way of inspecting the tracks was just walking around. And we can tell this solution was a kind of technological disruption. It changes the things, the way the things are done. And what was important, we had a short time to market to develop this solution. So the project was completed. This part related to detecting damages was completed just in 4 months. So maybe you can see, maybe not, I don't know. But for me, it's pretty comparable, this situation, to the situation startups face. And just a summary, what was important for us in this project? The first element was definition of problem. And usually it's very, very important to define what you like to achieve. And in this case, it was very, very precise. Goldschmidt had even definition of all damages. It was really well defined. And what was very important, this bullet. Data scientists and railway experts needed to use the same language. So we needed to define what's damage for what's not damage, to define it in the way that algorithms could learn it. We needed to agree upon measurement of the results. From analytical point of view, we would use a different approach than a track inspector would use. So this was very important to agree how to measure the results. The second important point were data. We needed to have a big data set. The data should be annotated. Annotated, it means marked as damage, not damage. And it should be large enough, but foremost well annotated. For example, to mark small chip, bigger chip to use this data to teach an algorithm. And definition of the images can be really subjective, as you saw. So the second important point in this data area was to have the data diverse enough and representative enough to be able to teach the algorithm. And it was hard because you need to have a train with a camera and to go along the tracks and collect the data and manually annotate. So it was not like this to have thousands of images. So we could not tell, bring us 5,000 of images. Not that easy. So we needed to have a big enough data set, but not the data set of dreams, of data scientists' dreams, and the analytics area. As you saw this workflow, it was not just a black box. It had a couple of stages, and for each stage, you can choose a lot of methods possible. So we needed to think about how to optimize this flow and not overcomplicate. And the last point can be really important. Usually in our project, there is a small element, usually it's overlooked, when if you apply more advanced mathematics, in this case, it was a multidimensional optimization, it can radically improve the results. And usually it's a case in our data science projects. So that's all. If you need to contact me, you have my contact data. If you need to contact Mr. Marcin Kowalski from Goldschmidt, there are contact data. And that's all I wanted to say.